And here we go. Hello and welcome to this week's HSC seminar. Today, I'm happy to introduce our speaker, Jason Lowe, assistant professor from UC Davis, one of our nearby neighbors. He's in the computer science department. His research interests target important big end applications of big data analytics, involves new hardware, new software, improved systems to increase scalability. He's had a lot of interesting work he's done, including major contributions to Gem5, which a tool many of you have used or read papers from. And he completed his PhD at the University of Wisconsin. And previously, he was at Georgia Tech for his undergrad. So let's welcome Jason. Let him take it away.
Great. Thanks, Scott. Happy to be here. It is too bad that I couldn't just drive down and see you all in person, but next time. Okay, so today I'm going to be talking about some of our recent research on managing memory smartly. So this is a talk that I gave at the departmental seminar here, so it's a little bit high level. I'll try to skip over some of the stuff like what is a cache, but since there's just a few people here, please feel free to interrupt as we're going. We got plenty of time to have discussions. Okay, so let me dive in. Nope. There we go. Okay, so I don't think I need to tell you all this, but memory requirements are growing. So this is a picture that I stole from a website that did not render it nearly high enough quality, as you can tell. But it's showing the number of parameters for a number of different deep learning workloads over the past, this is just 3 years. And so the y-axis here is the number of parameters, and we see time across the x. And so as we go over the past few years, we've seen a huge increase in the number of parameters to, GPT-3, which has over 160 billion parameters. And, this was a couple of years ago. And so if we look at the things of today, we're seeing these networks with trillions of parameters. And these things, these parameters of the deep learning model need to be kept in working memory. They either need to be in working memory for doing inference, or those parameters, as well as a bunch of other data, needs to be in working memory for doing training. So we need lots and lots of memory in order to store, in order to process on these networks. And it's not just deep learning. Things like graph analytics, which Scott is quite familiar with, is now scaling to things like billions of vertices or trillions of edges. And so we need, terabytes in order to store all of this data. And importantly, all this memory must be working memory. It needs to be byte addressable. All of these algorithms that we've written for these workloads assume that we can, use byte addressability to the memory. And, in order to keep up with the more and more compute that we've been getting, we need low latency and high bandwidth. So again, I'm sure that I am preaching to the choir here, but over the past few years, so if we look at the past 20 years, our DRAM capacity has been growing, which is great. We can store more things in our working memory, but unfortunately, the DRAM performance has not been getting as much better. And so there's this gap between the DRAM performance and the amount of memory capacity that we have. But this gets even worse if we look at the performance of processors. So this is the number of transistors, not exactly performance, but it's some measure of that. And while DRAM capacity has grown by 30x over the past 20 years, CPU transistors has grown by 200x. So we're getting a lot more compute and not that much more memory capacity. In terms of performance on CPUs, that's not quite as much performance increase as the number of transistors, as we all know, but it's still a lot more than the performance increase we're seeing from DRAM. So where we got 15x performance increase in DRAM, we got 150x performance increase on our processors. So there's, of course, a huge memory gap. And as we all know, this is nothing new. I was able to find this picture from Hennessy and Patterson, I think the second edition in 1996, which again just shows this exact same picture. This really, the trend of the memory gap is not anything new. But I do think there's a couple of new trends that are happening today that require us to look at this memory gap and maybe be able to find some different kinds of solutions for it. So the first trend is new devices. So we have things like persistent memory, things like Intel's 3D Crosspoint, which I'm going to be talking a lot about in this talk, that promises a lot more capacity for the same footprint or for the same amount of dollars as DRAM. But it's also byte addressable. So maybe we can close that gap in the capacity space. And then as far as the performance goes, we have these new interconnects like CXL that allow us to rethink the way that we architect our byte addressable system. And on top of all of this, probably the most important is security. So more and more we need to be thinking about the security of our data, not just the performance. Okay, so in this talk, I'm going to first start by talking some about why in this new regime of high capacity devices and high performance needs, conventional techniques of managing data don't work that well. Then we're going to talk a little bit about some solutions that we've come up with, which kind of bring software into the picture to help us solve the problem. Talk some about security in these high capacity, high performance systems. And then hopefully we'll have a little bit of time at the end. And I'll talk some about my ideas on research tools and what we can do to make better research tools. Okay, so let's dive in to the beginning. So this is based on a couple of papers that we wrote at ISPAS this year, as well as the NVM workshop, about how current DRAM caches don't work very well in modern systems. So let's put this in context a little bit. Let's start with some marketing. So this is obviously a slide from Intel. Intel is claiming that Intel Optane, which is their 3D Crosspoint persistent memory technology, is the best for everything. So essentially, if you're unfamiliar with this, Optane is higher capacity than DRAM, but a little bit lower performance than DRAM. So it can sit in this memory triangle somewhere between DRAM and SSD. It's also byte addressable, and so you can put it on the memory bus, which is what Intel has done. So we're going to be concentrating on this type of Optane, where it's on the memory bus, and essentially it's being pitched as a DRAM replacement that happens to be a little bit slower. So what does this look like in a system? So as it's on the memory bus, this Optane or 3D Crosspoint, but it shares the bus with DRAM. And so you essentially take out half of your DRAM DIMMs and replace them with Optane DIMMs. And you can do this, and what it gives you is a lot more memory capacity. So a single Optane DIMM is up to like 512 gigabytes of memory, whereas DRAM is like 64 to 128 gigabytes. It also allows you to really increase the amount of memory per node. So on a single socket here, you're going to have something like 3 to 4 terabytes of Optane, but only 384 to 512 gigabytes of DRAM. To put this in perspective, the amount of SRAM on a chip is something on the order of 64 megabytes. So, conventionally we use SRAM to cache DRAM, and these are many orders of magnitude, more than 3 orders of magnitude difference in capacity. But now what we're talking about is let's use the faster DRAM to cache the data in Optane. And in this case, the difference in capacity isn't quite as much, and neither is the difference in performance. Okay, so this is the kind of system we're looking at. Now, let me take you back to Computer Architecture 101 and quickly remind you all how caches work. This might not be the most important thing for this audience, but I think we'll see why it makes sense in a second. So obviously, when we read a cache line, we're going to take the index, go to the index location, read everything out in parallel, and then compare the tag. If it's a tag match, great, we return the data. Similarly, when we write, we read everything out, we match the tag, then we can, if it's a hit, we update the data and write it back. Okay, so one more quick one. Now, what if it's a write miss? So in this case, we're going to pull all the data out. We're going to check the tag. It's a miss. Now we need to write back the old data if it's dirty. Then we can fetch the old data from memory, update that, and then finally update the cache. So if we look at this in a flowchart, so this is generally how most caches work. If you have a write miss to dirty data, you end up having to do 1, 2, 3, 4, 5 RAM accesses for your single demand request. But this is how we've always done things. So why is this not a problem today that we have to do these 5 accesses? So if we look at the way caches work on today's systems, these SRAM caches. So this is a die shot from, I think, an AMD Zen 2, zooming in on the SRAM cache. Let's see if I can find that mouse real fast. What we can see is that the state, so like the dirty or not, as well as the tags over here, are separate from all the data. And so not only is this high bandwidth and that it's running at the CPU clock rate, but also the tags and metadata are separated out from the data. And so if you're updating the metadata, for instance, updating the current state of something, marking it dirty, or checking the tags, that's not interfering with updates to the data that's in the cache. So all these extra accesses, these 5 accesses that we have to do for each demand request, is actually not quite that bad because all of this is off the critical path in some sense. Okay, but how is this different when we start looking at DRAM caches? So in DRAM caches, as I mentioned before, the way Intel has architected this, the DIMM that holds the cache is on the same bus as the DIMM that holds the RAM. So if you're doing a metadata update to say check the tag, you're taking away potential bandwidth from other demand requests to that DIMM, as well as other demand requests to the backing memory as well. Not to mention that now checking the tag or anything else takes 15 to 45 nanoseconds, since we're now talking about storing this in DRAM instead of in SRAM. And so all of these extra accesses, these 5 extra accesses that we have to do in the worst case for a dirty write mess, really end up impacting performance. I'll pause here because I've been going pretty fast and see if there are any questions or if anything I can clarify.
And if anyone has any questions, remember you all are able to either just speak up or put it in chat, and I'll politely interrupt Jason when it's appropriate.
Yeah, I have a question.
Yeah.
So the link on this slide says like the AMD Zen CPUs. Is this is that SRAM architecture the same for Intel CPUs or all CPUs?
The high level idea of separating out the tag and state from the data, yeah. So you usually have 2 separate SRAM structures. So you can access those in parallel, or just access the tag if you only need to access the tag and not have to activate all the data.
Okay, cool. Thank you.
Okay, great. So I'll continue on. So, I've been claiming that we have, like, in theory, all these extra accesses because of the way that we access these caches, but let's look at some real data. So we ran some micro benchmarks on real Intel hardware with these caches to test and see if our theoretical understanding of these systems actually matched reality. So what we see here, let's start with this purple bar, is the effective bandwidth that you see from the processor. So this is the useful work that's getting done. The other 3 bars are coming from performance counters at the DRAM, which is telling us the bandwidth for DRAM reads, DRAM writes, as well as NVRAM or persistent memory or 3D crosspoint reads and writes. So what this shows is that for a read-only workload, so this is all, we're assuming 100% misses here, and nothing is dirty, everything is clean. Every single read, for one effective read, requires 3 accesses to our RAMs. And so we're doing 1 DRAM read, 1 DRAM write, and 1 NVRAM read for every single access to memory. And so that means while the theoretical bandwidth of the system is something like 80 to 100 gigabytes per second, we're only able to see 20 because we're wasting all this time managing the cache. It gets even worse for writes. So here's a write-only workload. And so this means we're, again, missing all the time, but all the misses are now to dirty data. So now you can see this theoretical thing that I showed you before of those 5 accesses per request. So again, we have the purple bar is the actual demand requests that we're getting, and then all the other bars are these extra accesses that we don't really need, or showing that there are extra accesses. And so we actually do see that there's 5 accesses per demand request. And so it really limits the amount of performance you can get out of the system. Okay, you may say these are just micro benchmarks. Who really cares? You're never going to run any workloads like this. And so we also analyzed this with a couple of other workloads. So I'm going to show you graph analytics now. And in a few slides in the next section, we're going to look at training deep learning workloads as well. So for graph analytics, let's first start with something that fits within the amount of DRAM we have. So if it fits within the amount of DRAM, here we're looking at performance in terms of the bandwidth we're able to see at the memory controller, which is somewhat of a proxy for performance, not exactly a proxy for performance, but it tells us something. And when it fits within the DRAM, we're getting pretty good bandwidth in these systems, pretty good performance. Now, if we go instead to a workload that doesn't fit in the DRAM, so this WDC12 is a graph which exceeds the DRAM capacity, so now we're having to spill things from the cache into persistent memory. The bandwidth that we see plummets. So it's about 2x less bandwidth for PageRank, and similarly for these other workloads. So the amount of memory performance that we can see goes down significantly when we have to start actually using this cache as a cache. But this doesn't quite tell the total story of what the end performance is for these workloads. It's not exactly apples to apples since these are 2 different graphs. So let's look at the other aspect of this, which not only is the performance of memory, but then how much data has to be moved to and from memory. So if we look at this data movement, so first we're going to look at the total data moved when we use the persistent memory as another NUMA node. So this gives us the theoretical amount of data that each one of these algorithms has to access. So this is the total number of demand accesses. And you see for BFS, this is something like 10 terabytes that it needs to access in order to complete the BFS algorithm. Now let's compare that to when we use the DRAM cache or the DRAM as a cache. So this is what we're looking at now is DRAM is not a cache, and now if we look at the DRAM as a cache, the total amount of data moved goes up significantly. And so we went from about 10 terabytes for BFS now to what, 4, 6, 10, 12, or 15 terabytes. And so we're wasting a lot of this data movement. So when we use it as a cache, not only, as we saw here, did we get significantly lower bandwidth out of our memory system, but the algorithm actually required a lot more data movement. So there's a significant reduction in performance when we use this DRAM as a cache instead of using it more smartly. So to quickly summarize, hardware managed caches have been great when we're talking about SRAM caching for a much larger, much slower memory. But when we look at DRAM caches, at least as they exist today, the bandwidth utilization is really low when there's going to be misses in that DRAM cache, which if you want to use DRAM as a cache, you're probably going to be having misses. This is a lot because writing back dirty data is quite expensive. And it looks like there's quite a bit of room for optimization. So again, I'll pause for a moment if there are any questions on why DRAM caches suck in this case.
I have a question. Maybe you can choose to postpone to the end of your talk. So this is super interesting research. I'd love to have you measured it so concretely. I assume there's some parallels maybe to some of the concerns about using, HBM versus DRAM, kind of as another. If you want to defer this later, you can, but or I don't know.
Yeah, I can quickly say that, we evaluated Intel's Cascade Lake using DRAM as a cache for 3D crosspoint Optane. In that case, the DRAM and the Optane were sharing a memory controller. And so to move data from one to the other, you just needed to pull the data in from Optane and then put it back out on the same bus to go to DRAM. So in some sense, this was, in theory, a quite efficient process. When you look at the so Intel also has systems where you have HBM as a cache for DRAM. So Knight's Landing was an example, and I think the new Sapphire Rapids is going to have a similar thing as well. I had some work on that years ago when Knight's Landing first came out, and we found the same kind of things, except it was a lot worse. Because in that case, you had to go to separate memory controllers across the die. And so not only were you having to do all these extra memory accesses, but you were also wasting on-die interconnect bandwidth as well. And so that was even worse.
That's a really interesting insight. I would imagine that the shared controller would have been worse because you're sharing the memory bandwidth, right? But I guess you're saying that the on-chip interconnect is also an issue. That's a really interesting observation. Yeah, I mean, in both cases, it seems like the cache levels, as you mentioned earlier in your talk, there's not as big of a disparity in speed and capacity as you might see in SRAM versus DRAM.
Yeah.
Well, cool. This is very interesting. Thank you.
Okay, cool. Yeah, if any other questions come up, please interrupt. Okay, so let's talk about a potential solution here. And so this is some work that was published at ASPLOS 2020, which I am still incredibly disappointed I didn't get to go to Switzerland for. But so this was trying to use software to better manage the cache. So the key idea here is that programmers know a lot about their workloads, know a lot about how the data can be used. Although really, I don't want to say programmers because I don't think we need to burden the programmer with this kind of thing. So as a good computer architect, you should read programmers as compiler or runtime or the experts who are writing the kernels that are running on these accelerators. And as we just saw, these hardware managed caches suffer from having to track fine-grained metadata, having to do things on 64-byte blocks. And also, a lot of the reasons why the performance is so bad is because the backing memory ends up with fine-grained, unpredictable accesses. You don't know what you're going to evict from the cache, and it ends up mostly random going to the backing store. So what we do is instead look at the fact that programs operate on objects, not on 64-byte blocks. And we can exploit these statically predictable accesses to the objects to better move the data between these different kinds of memories. And it turns out that this is the way programmers program now. If you look at these deep learning workloads like TensorFlow, PyTorch, or OneAPI, this is how everything is done. Everything is done with tensors. You just move tensors around. And so this is what we're concentrating on. Okay, so what is AutoTM? AutoTM takes the fact that these frameworks set up a static compute graph, or in this case, AutoTM requires a static compute graph. We have a number of kernels that execute. So you have compute kernels that execute, and these kernels compute or communicate via tensors. So some kernel produces a tensor, and that tensor is consumed or read by some other kernel. So our goal is to minimize the total execution time of these kernels. How do we do it? Well, we can choose whether to place a tensor in either fast memory or slow memory. Then we can decide when to move tensors between fast and slow memory. And we set this up as an optimization problem. So we're going to profile the kernel performance with with the tensors in either persistent memory or DRAM, and then model the tensor assignment as an integer linear program, and just ask an optimizer to find the best solution for where these tensors should be at any time. So digging down a little bit deeper, so the first step is we profile each kernel. So we go through the entire compute graph for every single kernel and run it with tensors in either DRAM or persistent memory and all combinations therefore within that. And so we get this profile for the kernel, which says this is the performance of the kernel when these tensors are in different places. And I suppose a bit of a spoiler alert, kind of the big takeaway that we learned from this black box optimization approach is that as long as your output is writing into DRAM, your performance is pretty good. your performance only really tanks when your output is writing to persistent memory. And this is because Intel Optane, the write bandwidth is much lower than the read bandwidth. So we profile all the kernels, and then we can take the profiling information and put it into our ILP. So I'll briefly explain how we model this as an integer linear program. So our objective is to minimize the total amount of time for the computation. So this is the total amount of time executing all the kernels, which now we know what the execution time for every kernel is, depending on whether the data is in DRAM or persistent memory, plus the time to move things between DRAM and persistent memory. We constrain the amount of DRAM in the system as our main constraint. And so if you look at any one kernel execution time, there's only so much DRAM capacity that you have, and so only so many tensors can be in DRAM, and all the other tensors have to be in persistent memory. The other constraint that we have is we model each tensor as a network flow problem. So you have the tensor comes in where it's created. It can be created in either DRAM or persistent memory. It can move between DRAM and persistent memory, between kernels, and then it has to be consumed at the end. So you have one tensor that flows through the lifetime, or one token that flows through the lifetime of the tensor. Then with these two constraints, we can ask an optimization problem solver to just figure out what the best solution is. Okay, so if you want more details on the ILP, I will encourage you to go read the paper. My student is an optimization expert. I am not, but I can try to answer questions if you want. Okay, so I want to talk briefly about the results that we found. So we were running this in the same kind of systems that I was talking about before. So we have Intel Optane and DRAM in the same system. And we looked at mostly CNN workloads. So the CNN, we chose CNNs because these are something that has static compute graphs that we could easily represent with our optimization problem. And we looked at two different classes. We looked at these conventional workloads that have memory footprints in the 100 gigabyte range. And then also we scaled up these workloads much bigger to make sure that they don't fit within the DRAM cache, so we can compare against using this as a DRAM cache. So in this case, they're around 650 to 700 gigabytes of memory footprint. Okay, so this is a bit of a complicated graph. So here we're looking at the performance of Inception v4 with using 100% DRAM right here. So on the x-axis, we have the amount of DRAM that we're giving the system. And then on the y-axis, we have the slowdown. So 100% DRAM is 1, no slowdown. Now we can make the DRAM limit as small as possible, run this. So this is now essentially using 100% persistent memory. And we get a slowdown of about 4.5x. So essentially, this is saying you don't want to just use persistent memory naively. You don't want to take a 4x hit on performance to maybe save 2 to 4x on cost. This would not be a very good pitch for Intel if this was the performance that you would see. So the question we asked was like, can we give it, or how much DRAM do you need to give the system in order to get most of that performance back? So since we're modeling this as an ILP problem, we can actually sweep this entire range and kind of see what the performance of DRAM is. And remember, at each point, we're finding the optimal solution to where you should move your memory. Okay, so this is what it looks like. And what we found is that there's this magic point here with just a little bit of DRAM. We don't need that much DRAM to gain back almost all the performance if we were operating 100% out of DRAM. And this is essentially where we have enough space such that you can output everything to DRAM and then copy it to persistent memory afterwards. And this is mostly, again, because persistent memory, Intel's Optane, performs poorly when you're doing random writes, whereas if you do sequential writes, you can get better performance out of it. So during the random write phase, we do that into DRAM, and then we copy that data in persistent memory. Kind of as a side note, this is a similar thing as to what Julian Shun and others have found with graph workloads too. So they have there's a project out of MIT called SAGE where they do essentially the same thing. They do all the writing to DRAM and then copy the results to persistent memory to save space. or to save performance. Okay, so this is with the kind of conventional workloads, and they all look kind of similar. But what about using the DRAM as a cache? So here we're comparing the performance of AutoTM, or automatic movement, software-based movement, to using DRAM as a cache. And so for these workloads that don't fit within the DRAM, we can get quite a significant performance increase by managing the data movement with software compared to managing it automatically in hardware. So in the best case at DenseNet, we get about a 3x performance over the hardware cache. And so this again is showing that the DRAM cache isn't great, but if you're really, if you're smart about it, you can use software to do a much better job of moving this data around. Okay, so why does AutoTM win so much? Or maybe really the question is, why does the DRAM cache lose? And so we kind of found three main reasons why the DRAM cache doesn't work very well and doing this software data movement is better. So first, the DRAM cache in these systems is direct map. So that means we end up with a lot of conflict misses. A lot of cases where if we had an associativity of 2 or 4, they wouldn't be misses. But it's direct map, so they end up being misses. And you might ask, well, why did Intel implement a direct map cache here? And that's because increasing the associativity for a DRAM cache is very difficult, especially if the cache is 384 gigabytes, which is the one that we were using here. Second, as we saw in the previous section, bandwidth between the DRAM and the persistent memory is really poorly utilized whenever you're missing in the cache. You end up with a lot of extra accesses, as we saw before. But the other thing, as I mentioned, is that the traffic ends up poorly shaped. When you're using DRAM as a cache, you end up with random writes to memory. Whereas if you're more smart about it, you can do sequential writes, which is much better performance. And then the last one, which we were a bit surprised about, although maybe we shouldn't have been in retrospect, is when we're managing this with software, we can take advantage of things about the workload that there's no way the hardware could know. So for instance, when you're training one of these big deep learning workloads, you end up with, like, say you generate some activations, and then you do your backwards pass and you compute the gradients, and then you no longer need those activations that you generated. Now, to the cache, those activations are dirty data, so it has to write it back from DRAM to persistent memory. But AutoTM is smart enough to say, oh, we're never going to use that data again, so we can just poof it out of existence and not have to do that extra data movement. So we can actually save, by using software, we can save data moved as well as do it more efficiently. Okay, so to quickly summarize this part, AutoTM is a compile time technique which exhaustively profiles kernels and uses an optimization, integer linear programming, to assign the data movement. We also evaluated this on CPU GPU systems. So having the main memory be the GPU DRAM and then the CPU DRAM be like the backing RAM. And so we're using the GPU DRAM essentially as a cache, and used AutoTM to move the data between the CPU and GPU. And that also worked very well. So these kinds of programmer-directed techniques can also work in other situations. But there's some limitations to AutoTM. So one is that it only works on static compute graphs. So things like RNNs or other kinds of workloads that have data-dependent data movement don't work with our optimization technique. The optimization technique in interlinear programming can be pretty slow, although if you're going to train for a week, it's kind of okay if it takes 2 or 3 hours to compile. And the other limitation is that all the data movement was synchronous. So we'd run the kernel, stop the world, move the data, run the next kernel. And so we're leaving a lot of performance on the table where we could be overlapping moving the data with actually doing compute. But the current Intel systems, it was actually less performant to try to move the data in parallel than doing it synchronously. All right, so I'm going to pause there for a second, see if there are any questions or comments on AutoTM before I dive into security. Okay, sounds great. So the next problem, how do we secure all of this data that we are now storing around? So this is work that's based on an IPDPS paper that came out last year and is a collaboration with colleagues at the Berkeley lab. So not only is data capacity growing, but sensitive data capacity is growing as well. And there's lots of data which is sensitive. So you can think of like health data, personally identifiable information, proprietary data that people might want to compute on, but they don't want to give everybody easy access to. So examples are things like the Million Veterans Program, where the DoD has all this health data on veterans, and they want to be able to give this data to data scientists to try to predict medical outcomes. But it's very difficult to do this because this is very sensitive data. There's also the Million Genome Project in the EU, and I'm sure you can come up with other million idea projects that would go here as well. So we want to give easy access to this kind of data to data scientists without allowing anybody to see it. And we also need really high performance. We want to be able to run these machine learning things or other kinds of data science workloads on top of this data. So here's a picture from Sean Peiser, our collaborator at LBL. He has a really great overview of this in CACM earlier this year. So this is essentially what our threat model looks like. So you have this encrypted data repositories that you want to give some data scientist access to. This data scientist wants to run some kind of high performance compute things, so maybe using something like NERSC at LBL on this data, produce some output, and then give it back to the user. Now this kind of at the output policy and things like differential privacy to make sure that the user doesn't get too much information. We're going to ignore this for now and concentrate more on this side of the equation, the compute system and getting data. So our threat models, essentially, we don't trust other users of these compute systems. We don't want other users to be able to see the data. And interestingly, we also don't trust system administrators. Now, it's not that we think sysadmins are going to try to hack in and steal our data. It's that the data providers, either because of regulatory reasons or others, don't want it to be even possible for the data science, for sysadmins to see it. So for instance, NERSC can't host health data. It's just impossible under HIPAA for them to host it as it is now. So if we're going to simplify this model a little bit, we have the data providers which trust some data scientist, but they don't trust the compute provider or other users. Now, if you squint at this, it ends up looking a lot like the threat model for trusted execution environments. So in trusted execution environments, these are hardware environments, hardware security solutions, which essentially take a process and puts it on steroids. So you end up being able to completely enclave off some process where neither the operating system nor the hypervisor nor anything else can access the data. So enclaves are protected from the operating systems as well as other processes. And there are lots of examples of these that exist today, from things like Intel SGX and SEV to ARM Trust Zone. ARM just came out with a new one called Realms. And even RISC-V has an open source version of a trusted execution environment called Keystone. So the question that we asked is, if we were to use something like a trusted execution environment in order to secure this data, could we still do scientific computing workloads and get the performance that we need? So we analyzed two different Ts that are kind of at opposite ends of the spectrum in terms of how they're architected. One of them was Intel SGX, and the main thing here is that in SGX, you have to separate out your program into a trusted and untrusted portion, and that trusted portion is quite small. You can only use like 94 megabytes of memory for it. AMD SEV, on the other hand, in this case, you're encapsulating an entire guest virtual machine as the trusted component. So this allows you to run things up to the size of the RAM in your system, but the trusted compute base is much larger. So we evaluated a host of scientific computing workloads from traditional HPC to modern HPC on these systems. We looked at a variety of different AMD systems as well as an Intel SGX system. So let me just give you a quick highlight of what we found. So first, we're going to look at the performance of these workloads running in SGX compared to running on the base hardware without SGX. And so on the y-axis, we see slowdown. And this is not percent slowdown. This is slowdown X. So CG is 75 times slower when we run in SGX than not. So really what this is showing is that SGX is just inappropriate for HPC workloads. This is mostly because of the limited memory that it has. So they only have access to like 96 megabytes of secure memory. And if you go beyond that, which every scientific computing application I've ever heard of does, you end up having to essentially swap pages in and out, and that really hurts performance. Additionally, thread scalability doesn't really work in SGX. Going from one thread to anything else doesn't give you very much speed up. And so again, it just doesn't work very well for these scientific computing applications. So SGX doesn't work, but what about SEV? So here we're going to look at the slowdown of SEV on a system. So first we're going to add just virtualization because SEV requires that you're running in a virtual machine. And then we're going to add SEV on top of virtualization. So when we add virtualization, there's a little bit of a slowdown, which isn't too surprising. We all know that there's a lot of things that cause slowdown with virtualization, especially for these workloads. I think we're seeing TLB misses and longer page table walks. But you might expect that SEV wouldn't add very much performance overhead on top of that. However, that is not what we saw. We saw significantly more performance degradation when we added SEV. So this surprised us, and we dug into it. So it turned out that when we run these workloads with just virtualization, and we look at the memory allocation over time, we found that this memory allocation was being allocated essentially randomly across NUMA nodes. However, when we turned on SEV, we found that all the memory was being allocated in one NUMA node. And this was hurting performance because we weren't able to get the bandwidth of the entire system. So the reason for this is when you start something with SEV, you have to pre-allocate all the memory you're going to use and then encrypt all that memory. And so since this is happening at startup with a single thread, it ended up happening on a single NUMA node. And then that memory got stuck there because since it's encrypted, there's no way the operating system can move it or the hypervisor could move it. And so we got poor performance. So what we did was manually make sure that all this data was spread between NUMA nodes. And when we did that, we found that the SAV performance was essentially no overhead at all. In fact, it might be slightly faster than the native case without NUMA interleaving. So this looked very promising. So now that we looked at the traditional HPC workloads, we looked at more modern applications as well. So these are graph workloads, as well as some other things from the DOE proxy apps and other workloads that were interesting for doing secure computing, like genomics workloads. And what we found is that SAV had much less slowdown than SGX, so up to about 2x slowdown. But unfortunately, it still has some. And the root cause of this is virtualization. So you can see where these orange bars, which is virtualization only, are about the same as the green bars, which is virtualization plus SEV. So almost all of our overheads are just coming from this virtualization. So in a perfect world, if we had something that gave us the kinds of security as SEV without virtualization, we would have almost no overhead. Okay, so to quickly summarize, SEV shows little performance degradation if used correctly, but with irregular workloads, it still has some overhead. SGX is just completely inappropriate for scientific computing. And kind of thinking to the future, we need something new and different, which combines the security, the way that SAV works from a security point of view, but doesn't have virtualization. Any questions there?
I think there's a question from chat. I don't know if you can see that.
Yes. Give me 1 second. So Jason asks, for problems at 1 million veterans, is the DoD willing to accept a T where the root of trust lies in a company like Intel for SGX? That's a good question. I don't actually. So I think in that case, since it's health data, it would probably fall under like HIPAA, whatever HIPAA says they're allowed to do with that data. I actually think the answer is probably yes, because at some point you do have to have some root of trust in any kind of system. But I don't know for sure. It's a great question.
I had one based on the gaps data. So I believe I saw larger slowdowns for SSSP. Were you able to diagnose what features cause that?
That's a good question.
Well, so maybe we can figure this out together. So I mean, so I wrote that code, and so I'm guessing compared to the other kernels, it's a lot more thread synchronization. It's like way more barriers.
Yes, that makes sense. Because that was the SEV or the virtualization overheads were twofold. One from extra page table walking time, and the other one was from synchronization. Synchronizing on AMD's virtualization extensions is expensive.
Yes, I don't know exactly how I know it's compiled down, but yeah, that particular code on the road networks can do a lot of barriers, and so how do barriers in OpenP get mapped? Yeah, that sounds like okay, cool.
No,
I was just curious.
That definitely makes a lot of sense.
I want to make that code go faster because everyone tells me this goes slow. I'm like, oh no, what do we got to fix? And so yeah, the high barrier count for SSSP is something that is kind of inevitable, but yeah, it's another reason why we got to fix that. Good.
Yeah. But I think my takeaway from this is let's not use virtualization. Let's try to get back down to the bare metal and try to give the same performance as native.
That would be great. Cool.
Okay, great. So let me try to bring this all together a little bit because I know security was a little bit out there. So the kind of vision that I have for the future here is that we're going to have these nodes with lots of cores, some local caches, maybe some local memory. And in the future, these new kinds of interconnects like CXL that are connected as well. And you can imagine these CXL things connected to these disaggregated RAM pools. And then maybe, so you can have really big capacity. And this is where the industry is going. It sounds like on Sapphire Rapids, for instance, Intel is not going to have 3D crosspoint on the memory bus. It's going to be on the CXL memory. Similarly, I know like Rambus is putting a lot of effort into these CXL things. But what if these RAM pools could be shared between lots of nodes? So now you can kind of get both scale up and scale out by disaggregating your memory and potentially sharing memory between nodes. What we're going to need is some kind of data enclave which can extend beyond the node, which none of these can do today, which gives you, global permissions as well as attestation across these nodes to make sure that the right user can access the right data. So if you have sensitive data here, you might want to cache it locally as well. We'll have to figure out how to do that, how to share sensitive data between things, or even storing lots of different kinds of sensitive data on the same pool. Lots of interesting problems here on how to do this. So we need some kind of security manager that's running at a higher level than all these other operating systems to work together. So the other thing is, of course, now we're talking about even more heterogeneous memory than what we have before. And so we need some kind of intelligent data movement. We need to be able to cache this data locally, either on the CXL interconnect or within your local nodes. We need to somehow keep this coherent. And I think really the only option here is some kind of software help, like what we saw in AutoTM, where when you manage this data with software, this data movement software, you get much better performance. Trying to manage things at a block level or even a page level is going to be painful and it's going to be slow. So I think software help is kind of important. Okay, am I out of time? I think I got like 5 minutes left.
I would go ahead and think 5 more minutes. Yeah, that'd be great.
Okay, cool. So let's talk about something completely different. So for all of this work, we had to develop research tools in order to do it. Now, as Scott mentioned at the beginning, one of the things that I work on a lot is Gem 5 and developing research tools. Although all of this work that I talked about here was done on real hardware, but we also had to develop a bunch of tools there. Things like AutoTM, all the code to actually run those deep neural networks, we had to develop before we could do it. So I'm going to really briefly, in 5 minutes, go over this talk. I gave it at Nope this summer, which I think might have been recorded. I'm not sure. But I have a lot of experience developing bad tools. So let me tell you all about how to develop a bad tool. So first, to define a tool, that's basically what we do in our research. It's where we spend all of our time, right? It's the infrastructure or artifacts that we develop. It's all the stuff that we need to make a paper. And it's what we, especially as architects and systems people, spend all our time on. So what's the goal of a good research tool? I would argue that the goal is impact. The goal is to maybe have a bunch of citations or have people build on top of what you've done. Or maybe even the goal of a good research tool is to transfer that into industry and have impact in industry. So these are our goals. With that in mind, let me tell you my experience of how to develop a bad tool. And then after I tell you about how to develop a bad tool, we'll talk about how you can develop a good tool. Okay, so number one, create in-house tools. Because whatever idea that you have to go along with your tool is good enough to have impact on its own. No need to have impact from the tool. Others can easily build off your ideas. It's super easy to recreate all the details of a tool from a paper, right? Plus, funders really love it when we just recreate someone else's work so we can compare to it in our paper. There's no need for anybody to reproduce your results. Why wouldn't they trust you? And plus, keeping it in-house gives you a competitive advantage. And what is research but a zero-sum game? So number two, don't follow software best practices. No one's going to see your code. It's okay if it's ugly, right? We call it research quality for a reason. Who needs version control or writing tests? And, most importantly, don't ever write documentation, right? You're the only person that's going to use this tool anyway. It's in-house. You're not going to share it. You're going to remember all these details in 3 years and you have to come back to it at the end of your thesis anyway. Number three, if you are going to give your tool away, make sure that it's open source. Do things like ask people to register before you give them the code. People really love filling out web forms, so ask them to fill out some more. Provide them a tarball. No reason to host on GitHub or anything like that. Tarballs are good enough. And most importantly, don't license your code. No need to put a license in there. Or if you do use a license, and I'll probably catch some flame for this, but use the most restrictive license you can find. GPL is really great because it forces other people to do exactly what you want them to. Number four, don't market your tool. There's no need to come up with a good name. Googleability just doesn't matter at all. There's no need for anybody to find it. Don't create a web page. Domain names are really expensive, and it's really hard to work with IT to get a website up. And there's no reason to provide context beyond the paper anyway. Papers are great documentation for the tool, and everybody loves it when PDFs are behind paywalls. So they can find out about your tool by going to IEEE Explore, which is inevitably down. And finally, most importantly, stop supporting the tool. Once your paper is published, there's no need to continue working on your tool. You've got everything you need out of it. Since the paper is accepted, that means the tool is perfect. The community has spoken, right? Plus, no one's going to need help using your tool. You wrote it. There's no bugs. And, people love it when there's links to dead web pages and extra points if that web page looks like it was created in 1995, which I think we've all used tools that do this. Okay, so I went through that really fast. Let me try to give you some ideas on how not to develop a bad tool. So do share your tool. Let others use your tool and develop on your tool. This is a way for your tool to have more impact. If other people use your tool, you're going to have more impact. And share it as widely as possible. Make it open source, put up a website, write tutorials, use it, write books, create videos on YouTube, these kinds of things. Any way you can get your tool in front of people will make it have more impact. Make sure to always follow software best practices. You want it to be easy for people to use your tool. Use Git, use good design practices, try to use Agile as much as you can. Do code review, these kinds of things. And this is something that I've learned over the years is from developing a lot of these bad tools, is try to use the tool, when you're building your tool, the tool that you want to use, you should pick the most popular one. So like if you're trying to pick a version control system, pick Git. That's what everybody uses. If you're looking for a language to develop it in, try to not pick the hot language of today, but the most popular language. When there's more questions answered on Stack Overflow, people can get help more easily, and that makes your tool more impactful. And finally, support the tool in any way you can. Try to answer questions before they're asked, provide good documentation, and always develop it after the initial release. There's always bugs, always ways it can be improved. And if you want your tool to have lasting impact in the community, you need to continue developing it. Okay, and with that, I have a lot more to say about this developing tools, but I think we are out of time now. So I'm going to skip ahead to the conclusions. Maybe.
You can take questions along the way, so we have another minute, but yes, we can go to the end too.
So I have a question about the memory, the fastest load memory that you were having before. One thing that they used to have on the old HGI machines, it was the attraction memory. So it's like a TLB manage and you see activity and then migrate. It was mostly to migrate local. So what you tried was more static, if I'm correct. Yes. Have you played with a little more dynamic and tried to use performance counters and then allow the OS to migrate between fast and slow? Have you seen about that option?
Yeah, that's a really great question. So we have investigated OS support. So there's recent work out of Abhishek Bhattacharjy's group at Yale optimizing the page migration support for 3D crosspoint or for heterogeneous memory devices. Now that wasn't exactly doing the attraction memory implementation, but it turned out for that it performed as bad or worse than just the default Linux NUMA when you put it on a realistic 3D crosspoint system. And I think that the reason is that, especially for these kinds of workloads where we're looking at that have working sets in the hundreds of gigabytes to more, it's really hard for the OS to react to anything. You really need those like software hints in order to move the data around, if that makes sense.
Okay.
Yeah, that's a really good question. I need to go back and reread that again, actually.
Maybe we'll let Jason conclude, and then we'll take any last questions.
Sure. Okay, so real quick conclusion. So as we all know, the memory gap is continuing to grow. But I think unlike the past, or maybe like the past, it's always been this way, naively applying yesterday's solutions aren't going to work for the way the memory gap is growing today. We need new kinds of ideas. And I think that the future is really this hardware software co-design. Specifically, we want to involve the program, not the programmer. So finding ways to do this at the compiler level or the runtime level is really important. And what we can do as we're designing these new kinds of interconnects and new kinds of memories is start thinking about how to co-design them with the data movement and data security so that we can have the programmability that we have from hardware managed caches, but with the performance of doing all of the management in software. And of course, I need to thank everybody who did all the work here, which this is pre-pandemic, so the group has changed quite a bit over the past couple of years. But yeah, the Davis Architecture group should take all the credit here.
Well, great. Thank you for a great talk. It's super interesting. I'll be quiet and let the students speak up with questions, or if you want to use chat, they can.
You got a quiet bunch that really like the black squares.
Yeah, no, we don't have a lot of webcams in this seminar, unfortunately, usually, but we're happy here. Maybe I'll slightly also elbow my colleagues who came in during your talk. And if you know Jose Renau or Heiner Litz, who both joined in, I'm sure they also were enjoying this talk.
So a little bit evolution on the question, the attraction memory, since there are no other questions.
Yeah.
I'm not so sure the current CPUs, what performance counters do they let you have per page? So I know that in the old MIPS, they have a special counter, so in order to do attraction memory efficiently.
Right.
But an ARM is having some new performance counters on the latest CPUs, but I'm not so sure what Intel has or have.
Yeah, they don't have any. I mean, they have 2 bits. They have the accessed bit and the dirty bit.
Yeah.
It's really not
utilization and try to rank the pages based on utilization or anything like that.
Yeah, I think one of the really interesting things that we've been thinking about is how to combine some of the software managed hints with potentially other kinds of hardware performance counters. And if you could see in ask at certain points in your software, like say when a kernel finishes executing, if the software can ask, did this page get dirty? That would really help a lot with the management and could allow us to do things very efficiently. I guess the other thing I'll say about operating system management is we found that I'm just going to really strongly advocate for software help here. There's just so many things that you can do from the software runtime that you can't do when you're oblivious to things, like this poofing things out of existence. When you know that even though the data is dirty, but you know it's not going to be re-referenced, which is something that happens a surprising amount, especially in these iterative kernels. Only in software can you elide that right back. Those are things that would be very difficult, if not impossible, to do if you have an oblivious system like in the operating system.
The operating system, for example, you do the allocation in a memory map. When you deallocate the memory map, then it's gone. You don't need to write back.
Yes. But then you get the problem of having to do allocation and deallocation in the operating system every time. We found we're working with another network, DLRM, the deep learning recommendation engine from Facebook, and we switched their code from doing allocations on every kernel invocation to making one big giant allocation and then reusing the data, and got like a 2 or 3x speed up from not using the operating system. So yeah, I think that you're right, Jose, that you could be, okay. I think you're completely right. And what we've done is essentially implement that kind of thing, but in software or like in the runtime instead of in the operating system, because the Linux kernel is really inefficient. Probably ways to optimize Linux too, though.
I have another question because the data that you were training was a bit confusing to me. It's not that I like to use the DRAM for keeping tags, but in one of the tests that you were doing, it was doing sequential access. If you are doing sequential access, I would have expected that a request to the tag will bring several tags, and then there will be cache on the cache. So there will not be a 1-to-1 ratio, so that it will be one tag access and it will bring several tags. And because it's sequential, then I don't have to send another tag request. I'm not so sure what's the size of the tags that you're going to have, but it's not going to be a full cache line. So why did I miss that on the plot, or why is not happening that thing?
Yeah, that's a really good question. You didn't miss it. I completely glossed over it. So the way that Intel's DRAM cache works is like the Qureshi Lowe alloy cache. So you have one tag and then one 64-byte chunk of data. And so when you do your DRAM, and actually the tag is stored in ECC bits in the DRAM. So you only need like 3 or 4 bits for the tag. You don't need very many bits, so you can hide those in that 8 bits of ECC that you have. And so you do one burst and you get one tag and one thing of data. And so, yeah, other tags might be in the page buffer, but you don't pull multiple tags across the bus at a time. We could argue whether that's a bad design or not, but that is the design that they chose. Does that make
Maybe
sense?
the next PIM application is tag checking for your NVM, right?
Yeah. It turns out, when you start to do more complicated things, like even something as simple as one tag per block stored together, moved across the bus at the same time, because misses take so long going to NVM, you have this really big window of opportunity for transient requests to happen, which can really break things if you're not careful. And if you start managing things more complexly, like storing multiple tags together or having an associative cache and these kinds of things, that window of vulnerability is only going to grow. And writing a cache manager to do that, which is correct, I think is very difficult. It's like the cache coherence problem, except now you're limited by a small amount of SRAM and your latencies are much higher.
It sounds like good insight. I mean, I think you're right. There's some sort of atomicity concern about, keeping the light data together so that way you don't separate it.
Yeah, and going back to your question about HBM, this is another case where HBM is worse. Using HBM to cache DRAM is even worse than using DRAM to cache 3D crosspoint, because now the bandwidth you have to support in these structures at the memory controller or at the caching home agent, you can have so many outstanding requests that you don't know whether they're a hit or a miss yet. And so you have to have a buffer for every single one of those requests. So you can use Little's law and see that you all of a sudden need, like your MSHRs, you would need thousands of MSHRs in order to support the full bandwidth of HBM, which is another big cost.
Yeah, I was just an application programmer trying to program nice landing at LBL, and yeah, it was annoying.
I mean, that's why they have that chicken switch where you can turn off the DRAM cache, right?
Yeah. Great. Maybe we'll give the students one more chance to speak up, or maybe Heiner, who came in. Okay, well, maybe we'll give Jason a round of applause. Thanks again for coming. I'm gonna stop the recording.